All right, so today we have Animesh from the Torch Compile team, and he's going to talk about guards. Guards are an important concept in Torch Compile. Basically, there are some encoding of all the conditions that are encountered while tracing through a particular path in the program. And they're a pretty core concept in the Torch compiler. So, so Animesh is going to talk about how guards work, what they cost, and how to optimize them and how they are used for correctness. Go ahead.
Yep. Thank you, Avik. Yeah, so as Avik said, we are going to talk about guards today. Um, and this is a concept because Torch Compile is a JIT compiler. So in this video, we will basically try to build a mental model or programming model of how guards work. How do they sort of integrate into this Torch compile system? What are the ramifications of these guards? Like what is the runtime cost? What is the compile time cost? And then we will discuss some escape hatches to reduce or mitigate these overheads. Um, there's also this blog that I just published, so you can also go through this blog. What I'm going to discuss is gonna be present in this blog. Okay, so let's start with something very simple, and let's try to build an understanding of what's going on. Like, why do guards matter? Where do they come from? And yeah, let's take a very simple example, something like this. And I'm gonna just run the code with you to just see what's going on. So I already have this file in here, so I'm gonna just run this again with you. And what's going on in this? We just have a model that has a layer norms submodule, and then we have a global pair object, which just have two integers a and b. And we're just trying to compile this, nothing fancy going on. We have a tensor of size 48, and we're trying to use it. Um, in this talk, I'm going to use TL parse. You might not have heard about it, but if you have not, please use TL parse when you are working with Torch Compile. It's really, really cool. And I was just going to show for all of these examples, I'm just going to go and show how TL parse reports look like. So this is what TL parse looks like. And what I'm interested right now is in this graph. So when we ran torch compile on that example, it basically extracted this graph where we have a layer norm that we saw, and we have an add operation that we saw. And the add operation were two constants, 2 and 5.
Mhm.
So pretty straightforward. And if we think about sort of like if it's try to sort of build a programming model, it looks something like there's a user function which maps to a compile graph. So this is definitely incomplete, but we can start with this model this sort of mental model in our mind. But definitely this picture is incomplete, right? And the main thing that happens is that when Torch compiles the JIT compiler, so it is invoked the first time you see you call the compiler.
Mhm.
So it's actually invoked on this line and not on this line. So when it's invoked on this line, this means it's specializing the graph on the input X and whatever is present in this op mod at this point of time. And
So,
yeah,
I mean, so you're kind of executing the model, and as and when you hit these user functions, at that point, you would come like just in time compile that.
exactly. Yeah. So the point is just in compile. And then therefore the compilation is specialized for the conditions that are seen at runtime at
Okay.
that compilation. And this is where guards come in. So like basically whenever you have this compiled graph, there are some specializations baked in. And the idea is that there's all like when Torch compile created this graph, it made some assumptions about the inputs, and this graph is valid only and only if all of these assumptions are still valid.
Mm.
So let's look at the TL parse report again, and let's look at guards here. So we also have the guards somewhere here. Let me just search guards, and we have guard strings. And if you see, these are all the guards here. I know this is a lot to take in at this point of time, but we will circle back to it later. But we can check few things. For example, we can check that the there's a tensor match in here on
Mhm.
input x, and this is saying that the tensor must be of size 4 comma 8 and stride 8 comma 1. So the graph that is extracted by torch compile must is valid only and only if the tensor is of this size and of this stride. Similarly, if you look at the equals match here, it is saying that the global pair that we saw, it had two attributes, A and A and B are 2, and A is 2, and B is 5. And you can actually see it from the graph as well. In the graph, you see we added 2 and 5. And therefore, if you change these attributes, if you change, for example, if you change this value to 3 here, then this graph is no longer valid.
Right.
So,
So
so
yeah, so in a previous video we talked about like sort of like programming model for export, which is kind of similar. So I guess the one of the bits is that tensor match is not actually matching on the like the data of the tensor, right? So that would be kind of stupid. In
yes,
some sense, you want to generalize every time you're creating a graph. So, but for this compilation to be valid, you have to specialize on the shapes, at least for now, right? So that's basically what you're saying, and then
yes,
constants are specialized and so on. Yeah.
yes, exactly. Yeah. So, so there are some guards. So this picture that the mental model that we are building is incomplete. So let's try to refine this, and it looks something like this now. Basically, for each compile graph, we have some guards, and in total, this sort of makes a compile unit. And if any, and basically, this compile graph is valid only and only when all these guards are succeed or evaluated true.
Mhm.
So let's do something. So we've already discussed there's a tensor match, and as Avik mentioned, we guard on the shape, not on the values. So let's say let's take this shape, which is different, and then compile it again. So I'm
Yeah.
gonna do this here as well. So let's just do this, and let me fire it off again. Um, and yeah, so we do expect the recompilation here because 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 obviously this guard that we had is no longer going to be valid. So let's quickly check the TL parse. And here we can see one more compilation. So if you look at the previous one, there was only one compilation, but here there are two compilations. So you can also look at the recompile reason, and the recompile reason is what you would expect. That the tensor X size has changed. It
Mhm.
was at index 0, it was 4 and now it is 8. Um, so yeah, so it works. Um, so if we now continue building on the programming model or the sort of mental model that we had, this is still incomplete because each function is not just one compile unit, but actually it's a link, it's a list of these compile units where at runtime we basically walk this list of compile units. For each compile unit, we check the guard, and if the guard pass, we can dispatch that compiled graph. And
Uh,
yeah.
maybe in like a naive question here, but why a list and not a set? Is it like these are these guards not guaranteed to be disjoint?
So this is more of a implementation question. So they could, like, you could design guards in a manner where all the common guards are run first, and then you basically
Mhm.
run the differentiating guards. In that case, the structure could be different. Here we tried very simple structure where we go through linked list. Like basically, you have to start on some first compile unit, check
Mhm.
all its guards, and we will go over like how can we make that fast if it fails, and then we basically do it one by one. So this is just an implementation detail at this point of time, but yeah, you could have set, you could have different data structure
I see.
to.
But in the worst case, you will compute.
Yes.
multiple guards before you hit a particular multiple sets of guards before you hit on a graph that where the guards are true.
Yes, exactly. So in case of multiple compilations for a user function, the worst case could be pretty bad, where suppose you have 8 of these compile units, all first 7 fail, and even and then the eighth one passes. So you are running all the guards possible. Yeah.
Mhm.
So so this is I think that this is a good mental model to have. Like basically, a user function is mapped to a list of compile units. Linked list is an implementation detail, and we will sort of come back to it later on. One thing is we don't want to keep on recompiling. So there are some pathological cases where we might keep on recompiling, and we don't want that endless loop. So there is a config called recompile limit, which by default is set to 8. And the idea is that if torch compile keeps on recompiling a function 8 times, it says, oh, this function is not compilable friendly, and therefore let's just give up on this function. And giving up here means that we will fall back to eager. When you call this function again, we will see if for the first 8 entries any of the guards pass. If guards pass, we will dispatch a compiled graph. But if it doesn't, we will just fall back to eager. We won't attempt a new recompilation.
Okay.
So hopefully with this, we have an appreciation of what guards are and how they fit into the system. Now, I alluded to this before. If we look at the guards, there are so many. And this could be quite unsettling because our program was actually quite small. Our program was this, and it has these many cards. So why? Why so many cards? And I think the reason is that we want torch compile to be sound. And what we mean by that is that if a user can change some part of the model, and because of which the previously compiled graph is no longer valid, we must do a recompilation. And therefore, torch compile by default guards on every user controllable specialization. So let's take an example. So in this case, like your code was this, where you have a layer norm some module, and you could just do this. It is possible, though it's rare, it is possible you could do this. And
Mhm.
if you do this, the graph that we had in the beginning is no longer valid. So, and as a result, like this is just one example, but as a result, we basically guard on so many different things, and all of these things could be changed by the user. And it may seem overguarding at first, but to be really sound, you have to guard on all those things. Um, and this is basically a soundness overhead trade-off where we have deliberately chosen soundness, and because of this, it could have some performance overhead. And we will later go on how to mitigate these performance overheads. Like if you feel this is overguarding, there are ways to remove these guards and reduce the guard.
So in this particular example, maybe I missed it, but are is the graph depending on the EPS value?
Yes, yes. Because this goes in this.
Oh, I see, I see.
Yeah.
Yeah, yeah. Okay. So I see. Yeah.
So we can quickly run this as well and just see that the new thing has the latest graph has the right EPS epsilon.
Hmm.
Yeah, I think the point is made, so we'll just move on
Yeah.
to the
Sure.
section. Yeah, any questions, Avik?
No, no, that's fine.
So, okay, so let's think about what is the impact of having guards in this system. So there's compile time cost, which is like every time there is a recompilation, you trigger this whole torch compile pipeline. And torch compile is known to have high compile times. Recompilation is just making it more worse. There's runtime cost, as alluded before. You are running these guards. In addition, you are running guards on multiple compile units. This can be very visible. This typically this is fast, but it could be visible where you have models with very short inference times, and guard overhead becomes visible compared to the total inference cost. So
So this can happen even if the system kind of stabilizes, right?
yes, because torch compile by default doesn't know when the system is stable. You could run something million times and then you could do something like this.
Yeah.
So by default
Yeah.
it is still it doesn't know when it is stable. And by stable here means that we expect no more recompilations.
Right, right. That's what I meant. Yeah.
Okay, so I think just quickly let's double check the TL parts here. We expect three compilations, so 0, 1, 0, 2, and let's not worry about this one for now. And then we can look at the dynamo graph. This is 0.01,
Hmm.
different from 1e minus 5. Okay. Okay, so yeah, we discussed about compile time cost and runtime cost. So let's go into the compile time cost. And the idea is that guards cause recompilations. And how can we avoid those recompilations? So a very common thing is that your input tensor, its shape changes. So in the example that I showed earlier, we saw that the first compilation was assuming that like it inserted a guard where it assumed static shape that we will only do for it can only support 4 byte.
Hmm.
If you know that, oh, you have maybe like batch size which is going to keep on changing, you can prevent this sort of first recompilation. Sort of like the second compilation, you can just instruct the torch compile guard system that, oh, I'm expecting this batch size to change from here on. So
Hmm.
already use symbolic size instead of a static size for this dimension. And this could be done with something called mark dynamic. There's a very good documentation here. So I'm not gonna go into the details, but you can use this torch compile mark dynamic to instruct torch compile to do the right thing. I have seen users using dynamic equals true. Um, Dynamic equals true works, but dynamic equals true means you can make the whole model dynamic. Like you are just saying,
Yeah.
treat every dimension, treat every integer as dynamic, which could bring a lot more dynamism into the model that than required. You want your model to be almost like to be mostly static and maybe like a slice of it dynamic, because if it's static it's going to give you better performance. So this mark dynamic allows you to make only a slice of your model dynamic if you may, while the rest of the thing is static.
Yeah, so this is similar to other like program language compilers where the more you can know about types, for example, like if you have int arithmetic, then you can specialize. If you have like generic code, then it always goes through slower paths and so on. So okay, so just to clarify, so mark dynamic actually gives you control over specific dimensions. So you don't even have to make your whole shape dynamic.
Yes.
If one of the dimensions is changing, then you can, yeah.
Yes, so you can say mark dynamic. So for example, in this case, you want your uh, you want your just batch size to be mark dynamic. So you can do torch compile mark dynamic x0. So
Yeah.
this means only 0th dimension, which is a batch size here, will
Mhm.
be mark dynamic.
Mhm.
Okay. Then the second pattern that we have seen which causes recompilation is a constant that keeps on changing. So for example, here you are compiling a function with a constant c, but that c is a float which keeps on changing. And this will cause a recompilation because by default, uh, torch compile guards on the exact value of these constants. And one easy way to avoid this recompilation is to wrap this constant into a tensor. So you can do something like this, and this will just call one compile because we don't guard on the values of tensor, we just guard on the shape of the tensor, and therefore this will avoid compilation. So if you can change your model to do this, that's awesome, and that will give you so like that will remove the compilations from your model. Um, the third pattern that we have seen is NN module int attribute change. It's kind of similar to the previous one, just that now it's an attribute of the model. So for example, you have this constant, which is the attribute of the NN module, and then you keep on changing. So this could be maybe like something like a count, where you are counting the number of times um, you
Hmm.
have called inference or something like that. One easy way is to convert this into a tensor, like the
Hmm.
previous one. Or if you are like, if it's involved in the computation like this, you may want to make it a symint, a symbolic integer, so that like the down port gen does not assume the constant value. It assumes a integer which keeps on changing.
Yeah.
And to do that, you can use this config, allow unspecialization integer on an n modules, which will convert this C into a
So
symint.
in this case, it'll automatically consider constants to be Siemens.
By default, Torch compile considers it to be static, so it will call
Normal.
recompilations. But with this, it will make it a symint.
Okay. So yeah, I mean, the programming model here is like consistent. So basically, anytime you can hide things inside tensors,
Yes,
they will not be specialized. There are some default rules of like we specialize on constants or whatever. So you can use the tensor trick to hide or I mean symbolic ends are also like that, I guess. Like they're
yes,
they're they're not specialized. So yeah.
yeah. And then there's a fourth one, which is not really a workaround, but as mentioned earlier, we have a limit, we have a threshold on how many times we compile a function and then give up on it. This limit is 8 by default, but it is possible that you know that you have tried all of these above sort of workarounds, and then oh, you have a genuine reason that you should have more compilations. And in that case, if you want to benefit from those compilations, you can just increase the recompile limit. Use this sparingly. Like if you have a like open issues on PyTorch to see if we can not recompile this much. But in some cases, it could be a valid reason to recompile this much.
So just curious where the number 8 came from. Obviously, it's just like a heuristic, but is it like related to, okay, in other words, if a function has many arguments, wouldn't you assume that there could be many more recompilations than a function with fewer arguments? And in that sense, shouldn't the limit be sort of like scalable according to that kind of
It is
metric?
possible. It is possible. So, like going back to the programming model, what we have here is a function which can be mapped. Like for each function, we have this recompile limit number of cache entries,
Yeah.
and to keep the designs in. And like in reality, you just don't compile one function. You have basically
Right.
multiple functions, each function mapping to many of these compile units. So to be simple, we have chosen the recompile limit for all the functions to be same. Now,
Right.
what we are proposing is, can we have some sort of a configurable, or like a function which is supposed to have more recompilations, can have a higher compilation limit, recompile limit, while the other function can have smaller. I
Yeah.
think we can do that. It's an implementation choice.
Okay.
To keep things simple, we have kept it one.
And there is no like rotating cache or something like that, right? Where you kind of basically evict the first few when you see like new, you can still keep like 8 things in your cache, but you just evict the old ones and then keep adding new ones or something.
So we don't evict anything. We evict only and only when a, a compile unit is invalid.
Mhm.
A compile unit can be invalid. For example, for example, in this case, suppose you delete the module itself, like you call delete mod. So in this case, like all the compile units are kind of invalid,
Yeah.
because in the guards we will have like sort of weak differences
Yeah.
to these module, and
Mhm.
then we will do eviction.
Yeah.
Uh, but we don't do eviction for valid entries.
Okay.
Yeah. Um, yeah. So I think and another question, like why 8? So we earlier, like maybe like 1.5 years ago, this recompile limit was 64. And what was happening was that in many cases this would cause a really large compile time. relax compilation time, because we'll just like what we have seen is if we have recompiled 4 times, it's
Yeah.
more likely we are going to recompile to the limit
Yeah.
and something bad has happened. So to have a good user experience, we want it to be 8. In fact, we want it to be I want it to be 4, but then we found 4 is not good. So yeah.
Okay.
So 8 is to have a good default, but this is reconfigurable.
Okay.
Okay, so we discussed the compile time cost. The other aspect of guards is guard overhead, right? And and just to remind why guard overhead. First was why so many guards, right? Like we have a large number of guards, and we have these guards because we make a deliberate choice to be safe always, even though it can have high guard overhead. And the other reason is sorry, I'm moving a lot. And the other reason is this linked list of compile units, where we are walking through this linked list,
Mhm.
and yeah, we are executing many cards together.
Mhm.
So let's look at some examples and see what is this guard overhead, and how can you reduce this guard overhead. And if you ever have profiled a PyTorch program, you know about PyTorch Profiler. So you can just use PyTorch Profiler, and yeah, like the guard overhead is present under the event called TorchDynamo cache lookup. So uh, I'm going to I'm going to run this function while we discuss other things so that we can see what's going on. So yeah. So yeah, so here let's go through a different function. And the reason I chose a different function is somewhat more realistic, not very realistic, but somewhat more realistic. It's a nested module where we have a couple of linear layers, and then it itself has nested modules as submodule.
Mhm.
So the reason is just that when you create a model, it is basically a deeply nested submodule structure.
Mhm.
So I want to have guards that sort of represent or mimic this kind of a structure. Um, and yeah, and then you can run this, and then you can just do profile like this. And when you do profile like this, you get this trace.json file. You can open in Chrome tracing, and it'll look something like this.
Okay.
Uh, like you will see this box, torch dynamo cache lookup.
Mhm.
And let's see if that is finished. Okay, now if you give me a second, I will. Uh, So let's open Chrome Trace. And I'm going to use Perfecto UI because I like it more. And then let's bring that in. So downloads. Okay. So if we go there, we see this thing. And if I zoom in, this is the cache lookup. And then this is other part, which is a compile function, which is like the event for the whole of the inductor code, the sort of the backend of Torch Compile. I'm not going to go about other things, maybe some other video, but let's focus on the Torch Dynamo cache lookup. And in this case, we see 945 microseconds, roughly around a millisecond is spent in guard.
Mhm.
Um, this could be considered high. Uh, if like in this model, maybe it's okay because we have large execution time. But for your model, maybe this is very fast, and there the torch dynamo cache lookup is visible. So yeah. So so we have so the question is, can we reduce these guards? And today we provide two escape hatches to reduce this guard overhead. One is called skip guard eval unsafe, stands, and the other thing is called guard filter API. The guard filter API is work in progress. It's not present in 2.7 release. And even I think like some aspects of it might not be even in nightly. So please wait for like a couple of weeks for
Mhm.
fully use this guard filter API. But this skip guard eval and safe is present in 2.7.1, and then you can use that. So let's try to see what's going on with these different escape hatches. So I think as Avik alluded to earlier, uh, when when your environment is stable, we don't need so many guards. And when I mean stable, I mean you have run your model some number of times, or maybe like let's call it warm up. Like you have warmed up your model with enough representative inputs that you have seen all the compilations. And from there on, you do not expect any other compilation. You do not expect anybody to change your model in place. So in that case, if you have, say, four compilations, if you have like four compile units,
Mhm.
you need a handful of guards to differentiate between these four compile units. You
Yeah.
don't need all the guards. And then this is basically what skip, guard, eval, and save does. It finds out those differentiating guards and then drops everything else.
Oh, okay. So this is automatic. Okay. So yeah, because for a while I was like worried, okay, do you need to understand which cards to drop and not? But it just automatically analyzes the cards and okay.
Yes, yes, and it's really easy to use. You can use a stance, and maybe what a stance is a topic for another tutorial. But to use it, it's really easy. You can tell compiler to set the stance, and you are set saying that okay, just use skip guard eval unsafe. And when it does that, you can see almost all the guards are dropped because there's only one compile unit in here, and we treat the tensor guards as like important guards, so we don't drop them. So only what is running here is a tensor guard and nothing else. And if you see, this is 27 microseconds, which is like zero compared to 900 microseconds that we had here.
Okay.
So, so this is really cool. This is automatic. You might wonder why it's unsafe. It's unsafe because suppose after warm up you do this, and suppose in this line you
Yeah. Yeah.
basically change. You do mod dot layer norm dot eps equals 1e minus 5. Uh,
Yeah.
it is going to be silently using the wrong graph.
You drop one of the common guards that was always true, but you don't know in the future whether it could have been false, and then
Yes.
not, and that would have triggered a recompilation. Yeah.
Yes. Yes.
Yeah.
So, so this is like one of those cases where Torch compile by default is guarding on everything because it wants to be safe.
Yeah.
But for practical use cases, you're in many cases you're not going to change your module later on. So this is handy to reduce guard overhead. Um,
Makes sense.
yeah. The other one is guard filter API, and this is where you have to understand guards a little bit. What is the benefit of guard filter API over skip guard eval unsafe? It's basically I think it's more like in prod systems. So like in prod systems, you might have control over the code that compiles, but not at the runtime. So for example, in the case of skip guard eval unsafe, you have to warm up your model, then you have to set the stance, which means that you need to have some control over where to put these lines, where to warm up, and those kind of things. And you might say, no, I don't have control over the runtime, but I have more control over the compilation part. So this is where guard filter API comes in. When you're compiling, you can tell the torch compile guard system, oh, skip these guards.
Mhm.
And and the idea is very simple. Like you when you're compiling, you provide this hook in the guard filter string, like keyword options and guard filter key. You provide a hook function. This hook function takes in all the guards, and it basically returns a Boolean list where if it's true, we keep the guard. If it false, we skip the guard. So it's kind of very simple.
So,
Um,
the kinds of guards that we have, is that like a public API that is part of this thing? Like if somebody is going to implement a hook, like this function, right? It seems like a user level function, right?
yes,
So you
Yeah,
would,
it is not. It's something which is left right now for users to figure out themselves.
okay.
But it's a good point. We should make this make at least the guards types um, uh, more user facing. Um, what we are gonna do is gonna ship several ready-made filters.
Yeah, that makes sense too.
Like
Yep.
for example, have only tensor guards or
Yep.
like
Yeah.
have reject all guards on globals.
And
Um,
so then your hook is basically some kind of Boolean function on these filters or something.
Yes, yes.
Makes
So,
sense.
so what we think is that if we provide this collection of ready-made filters, that should suffice. But for users who want more control, they can write their own
Yeah.
filter functions as well. So in this,
Any quick time check. So the meeting is going to end in 3 minutes or so.
okay. Should be quick. Yeah, I don't need that much time.
Okay.
So here I'm gonna go over just two of these. So you have something called inbuilt NN module. Inbuilt NN modules like NN.linear, LN.linear norm. These are like inbuilt NN modules, and it's very unlikely you are gonna do something like
Mhm.
mod.linear norm EPS. So if you think your inbuilt NN modules are not gonna change, you can use this hook. And if you use this hook, we reduce from 900 milliseconds to 370 milliseconds. You can also say, oh, I'm not going to change any of the NN modules. Like if you have your own user-defined NN module, and suppose here, like you had something like self.c, and you know that you would never change mod.c. You could also skip all the guards on user-defined modules, and this is the second one. So if you do that, in this example, you have actually eliminated almost all the guards, and therefore the guard overhead goes to zero.
Oh, wow. Okay.
Um, yeah. Then there is some details on how guards are implemented and the sort of the engineering principles behind like how to make them fast. But that's not important. Maybe that's for readers who are interested in learning more engineering details. Um, yeah.
Cool. So among these, is one of the things that you're thinking of in like under the hood, like actually what we were talking about, where you kind of convert a list of guards into sort of like a tree of guards, or is that like too?
Yeah. So first thing is like, what's the guard structure? It's a tree structure. And then how do we make guards fast? We basically move everything to C code.
Okay.
And we basically use CPython APIs.
Yeah.
And the other important thing is fail fast on recompilation. So for example, if you have many compile units, you want, and if you suppose you're going to take the third compile unit, you want the first and second compile unit to fail fast. So what we do is the guards that fail, we move them early in the guard tree structure so that the next time the offending guards fail first.
All right.
Um, and the other optimization is basically you can also move around these compile units, and we use most recently used strategy to keep the compile unit first, hoping that yeah, this is more of an empirical choice that we have seen to work pretty well.
All right. So yeah, we're out of time. Meeting can end anytime.
Yeah,
So let's thank Animesh.
yeah.
Yeah. All
Thank
right.
you. Bye.
Bye bye.